Hey everyone, welcome to Toronto Workshop. This week we're joined by Amanda Coston, who is a postdoc at Microsoft Research, and she is an incoming assistant professor at UC Berkeley, where she'll be starting in the fall. Her research considers how and when machine learning and causal inference can improve decision-making in high-stakes social settings. So thank you very much for joining us, Amanda.
Yeah, thank you for the introduction and thanks so much for having me. I'm really excited to have a chance to share my research with you all and have a good discussion afterwards. Feel free to jump in with questions during the presentation, and then we'll also make sure to leave time at the end for some discussion. So today I'm going to talk about addressing validity in decision-making algorithms. And what I mean by validity here is the fact that a lot of times the way people build and evaluate algorithms is not necessarily aligned with what they want to do. And this can mean that the algorithm is actually predicting something different than what they think it is, or that its performance properties in the real world settings are different from what the evaluation would suggest. And this is common, and the reason I focus on this in decision-making settings, because that's different from a standard prediction setting. So in a prediction setting, you're not intervening on the system, you're just observing it and making a prediction about what's going to happen next. Like you could think about like stock market price predictions. Like we just want to know, are the stocks going to go up or down? But in the settings that we look at, we're interested in using the algorithms to make a decision, and that decision can affect the outcomes that we're trying to predict. So that's kind of the key reason why this is a little bit more challenging than standard prediction settings. And we'll use techniques from statistics, specifically causal inference, to address this. So at a high level, we'll start by formulating the learning and evaluation tasks for decision-making algorithms. So here we're going to kind of formalize the goals and when we want to build an algorithm and evaluate it. And before we even think about data, just write down mathematically, ideally what we want to do, and then we can start to think about how we can translate that to the data that's available. We will discuss why standard approaches that often skip this problem formulation stage can target the wrong quantity when there's this missing outcome data that I kind of alluded to, and we'll get into that into more detail. And then as a solution, we'll propose counterfactual learning and evaluation approaches that are adapted from standard techniques in causal inference. And the running example that I'll use and the data, the empirical results that I'll present are in the child welfare task using data from Allegheny County, their child welfare screening hotline. So this is just an overview of the papers that I'll mention, that I'll draw on from here today, as well as my collaborators. So we'll mostly focus on this paper in the top left, counterfactual risk assessments, evaluation and fairness. And if there's time, or maybe in the Q&A, if there's interest, there's another paper where we relax one of the kind of strong assumptions. So for most of the talk today, I'll make this kind of strong assumption because it will simplify things. But if there's interest in what to do without making that assumption, we could discuss the paper in the bottom right corner. Okay, so now with that preamble, let's get into the task of problem formulation. Okay, so we start with the goal. So in these decision-making settings, oftentimes the algorithm is tasked with making a hypothetical prediction. That is, we'd like to predict the likelihood of a downstream outcome if we take a particular decision. So as an example, in criminal justice, the goal is to predict the likelihood the defendant will recidivate if released. In the child welfare example that we'll focus on, they're interested in predicting whether the child would suffer harm if they don't open an investigation. And in consumer lending, the goal is to predict the likelihood an applicant will default if their loan is approved. And this kind of structure happens in a variety of other settings as well. You could think about in healthcare, oftentimes there may be a goal of predicting whether the patient would be readmitted to the hospital if an invasive procedure isn't done and they do a more lightweight procedure. But throughout all of these, there's this common structure that we want to predict the likelihood of an outcome under a particular decision. And this is a challenging thing to do because we have missing outcome data due to something called bandit feedback. That's just a technical term to say that we only observe outcomes under the historical decision that we took. So it's perhaps easiest to see this with an example that I'll walk through in the child welfare setting. Okay, so a call comes in to the child welfare hotline, an allegation of neglect or abuse, and the call worker is tasked with deciding whether this case, it seems that the child may suffer harm if they don't screen it in for investigation. And they're making that decision based on the information in this call, as well as in jurisdictions like Allegheny County, they also have access to an algorithmic prediction. And then, so they make this decision. They have two decisions available to either investigate the case or to screen it out of investigation. And we mentioned there's this concern about missing outcome data. So, okay, to see that, let's say the call worker decides to investigate the case. And as part of that investigation, they might determine that the family has food insecurity and potentially maybe the agency is able to provide services to meet those food needs. So then we could see a positive outcome after investigating. But counterfactually, had they made a different decision and not investigated the case, that is, screened it out, those food needs would still have been there, but would have been unmet. And so we may have observed a different outcome. And then, of course, the goal in this setting is to predict harm if not investigated. So that's the outcome that we're interested in. But in the scenario that I just presented, we said that this particular case was investigated. So we don't actually know that counterfactual outcome. We don't know what would have happened had they not done the investigation. So there's this question, what would have happened counterfactually had they been screened out? That is really important. Okay, so at a high level, we have these missing outcomes due to bandit feedback. And standard approaches that don't address this specifically can be misleading, and we'll see a little bit more of that. And then we'll introduce this counterfactual technique that we can think about as imputing these missing outcomes. And that will give us a valid procedure under some key conditions that we'll discuss. Okay, so to get into the specifics, I'll introduce some notation in this running example of the child welfare setting. So I'll use D to denote the decision taken by the human decision maker, Y to denote the observed outcomes, and then I'll use a superscript notation to distinguish these counterfactual or potential outcomes. So the outcome we would see under screen out is Y superscript screen out. The outcome we would observe under investigation is Y superscript investigation. Or if we want to leave it generically, I'll just write Y superscript D. And we saw already that those are not necessarily the same because the decision can affect the outcomes. And then I'm going to use the hat notation to denote the algorithmic prediction. So Y hat is an algorithm's prediction. And X to denote the information available to the call worker in making their decision. So our goal in this setting is to predict the harm if the case is not investigated. But another challenge that we won't really focus on in this talk, but is really important, is that we don't ever directly observe harm to the child. In these settings, we only have proxy outcomes for harm. So the one that we're going to use here is commonly used. It's whether the case is referred again to the hotline. So you can think about this as a noisy proxy for harm. And we're going to use 1 to denote that a re-referral happened and 0 to denote that there was no re-referral. Okay, so with that, all that notation in place, we can get into the interesting task of how to learn a predictive model in this setting where we have missing outcome data. So we're going to do this problem formulation where we start by saying, okay, so we have observed the outcome Y. We saw that in the previous slide. That's the re-referral, or in other settings, if we're looking at lending, that could be defaults. We have features available for prediction and the decision. Then our goal is to predict the likelihood of an outcome if a particular decision is taken. And we can write that in the notation that I just introduced as Y superscript D That's the counterfactual outcome, and we'd like to predict that using features X. So we can put that all together to say that our prediction target is the conditional likelihood of the potential outcome on features X. And then, so this is the goal. This is what we would like to build a model to estimate this quantity. And then we run up to this issue that YD is hypothetical, right? So those are those potential outcomes. We may or may not observe them depending on what decision was taken historically. So how can we proceed from here? We'll go through a process that's called identification. So this means that we're going to write this hypothetical quantity in terms of things we can observe in the data by making some assumptions. And a really simple way to do this would be if we assume that the decision actually doesn't affect the outcome for anyone. So this would mean that regardless of what decision we take, the potential outcomes are the same. So we can just use the observed outcome to figure out what our potential outcome would be. So if we think that that's true, then actually all of the issues that I'm motivating, the talk with today wouldn't matter. And we could just use the standard approach because that would give you the counterfactual one. So that's one way we could do the identification. In a lot of settings, it's pretty unrealistic. And I think certainly in the child welfare one, to assume that the decision doesn't affect the outcome. In the best case scenario, the investigation should hopefully reduce risk if the agency is able to provide services to meet the family needs. In other unfortunate scenarios, the investigation could actually increase risk because of the stress of having the child welfare agency involved in the personal life. But either way, it's kind of hard in that setting to assume that an investigation is not going to change the likelihood of harm or neglect. So we're going to try to make some other assumptions that might be more well suited to the setting that we're looking at. Okay, so our goal is to learn a model to predict the probability of the counterfactual outcome conditional on X. And the assumptions that we're going to use are, one of the key ones is that there's no unmeasured confounding. So this is saying that the decision is as good as random, conditional on the observed factors X. And this is an untestable assumption. We can't really use data to assess this, but we can reason about it given our particular setting. So in the child welfare setting, we have a pretty good sense of what information the call worker is using to make their decision. They're using the information in the call and the algorithmic prediction. So we may be pretty confident that if we can record all of that it's reasonable to make this assumption that the decision is as good as random, conditional on X. Another assumption that we'll make is called overlap or positivity. And this is assuming that all units have some probability of getting the proposed decision. So I'm using pi of X here to denote the propensity score function. This is saying the likelihood of getting treatment conditional on X. And we're going to assume that that's greater than 0. This is a testable assumption, so we can look at our data and compute this quantity pi of X and see if it's really close to 0 for any cases, then we might be concerned about violations here. And finally, we'll make another assumption, consistency, which is essentially assuming that there's no interference between units. So this is assuming that whether we investigate one family is not going to affect the potential outcomes of their neighbors. This assumption, I think that's fairly reasonable in our setting. It's a lot harder of an assumption to make in other settings if you're working like looking at vaccines, for instance. If your neighbor gets a vaccine, that is going to likely affect like how susceptible you are to disease. But in our setting, we're going to assume that there is no interference. That's also an untestable assumption that we just reason about. Okay, so then together, these 3 assumptions enable us to write this counterfactual quantity on the left in terms of observable quantities that we see in the data on the right. So the target that we want to predict, we can just write as the probability of the outcome conditional on X among those observed to get the decision of interest. And then this identification suggests what our learning procedure should be. We can train a model to predict Y, and we're just going to do this in the rows where we have observed the decision of interest.
Amanda, just a brief clarifying question from David Seymour, just from the chat. For assumption 2, is this a local assumption?
Local, sorry,
David,
could you?
David,
Yeah,
feel free to unmute
elaborate?
yourself and clarify.
Yeah, I'm just wondering if this can hold on a subset of the data and have the method be well defined for that subset.
Yeah, exactly. Yeah, that is right. So that is actually what we do in practice because yeah, so to make this a little more concrete, I can give an example. In the data, this violation is, there is a violation of this assumption when certain allegations are mentioned, like incest, because incest will always be screened in for investigation. And so we would see violations here, but for the purpose of building and evaluating an algorithm, it actually makes sense to just filter out that data and say, the human already knows what they need to do. There's a specific policy. There's no uncertainty about what decision to make. And so then we'll just focus on the cases where overlap holds and say that those are the ones where there is uncertainty and the human might want to have this algorithm help inform what decision to make. So yeah, great question.
And just while we're on here, Wijdan is a clarifying question. Might the consistency assumption be affected by scarce resources, for instance, the availability of investigative resources?
Yeah, so that's a good question. Yeah, it sometimes feels like that is at play here, but that actually isn't a problem. So if I'm understanding the question correctly, scarcity of investigative resources means like if I decide to investigate a family, I may or may not decide to investigate their neighbor because of the scarcity of resources, and that's okay. Because we're interested in whether the decision to investigate the first family affects those hypothetical outcomes. And those hypothetical outcomes are defined they're going to be defined and they're the same regardless of what decision we take. So this scenario, the scarcity of resources is going to affect the observed outcome because it's going to affect what decision we take for that second family, but it's not going to affect the hypothetical outcomes. And that's what this statement is really about, if that makes sense. Yeah, so this would be violated in the vaccine setting or sometimes people do studies in school settings where maybe you offer some resources to certain students. And if those students then go later study with other their classmates, then that could violate this assumption because the students that they're studying with, they weren't actually getting those tutoring or extra resources, but they're kind of indirectly benefiting through the other students. So if we translate that back to the child welfare setting, this would be like if, seeing a caseworker go into your neighbor's house makes you extra nervous, or your neighbor starts telling you the information they're learning from the caseworker, and that then affects your parenting strategies, then that would violate this assumption. Okay. Great. Okay, I'll move on, but feel free to jump in if there are any lingering questions. Okay, so with this identification, we've gotten to how we should train a model in this setting. We're just going to predict Y using only the rows where we observe the decision of interest. And we can look at how this differs from the typical approach. So what I have here in the top row is the procedure I'm proposing. And then I'm comparing it in the bottom row to a procedure where we just predict Y using all the rows. And I case these out by the different intervention type. so that we can see how these models differ. And so the interventions that I'm showing here, they vary in what we would expect to be low risk to high risk. So in green, we have cases that were screened out. So these are ones that the caseworker presumably thought were pretty low risk. Then in yellow, we have cases that were investigated. And then in pink, we have cases that were investigated and then where the agency offered services. And then in red, the one we expect to be highest risk were cases that were investigated and where the family, the child was then placed into foster care. So we have this ordering we'd expect from risk based on these human determinations of treatment. And we see the expected trend in our counterfactual model. The predicted risk is highest for these red and pink curves and lowest among the green. But we see something interesting in the bottom row. If we just built a model using all the rows in our data, we see that those in pink, the ones who received services, have the lowest predicted risk. And this makes sense if we think that those services were effective in mitigating risk, which we would hope, because they got services, so their observed outcomes would have been good because they got those services. But it would be ill-informed to use this model for future decision-making because we might potentially decide to screen out those people who would benefit from services if they were screened in. So this is some motivation for why this does make a difference in practice. Now, we also might be interested in kind of evaluating these two models in terms of standard metrics like mean squared error, calibration, accuracy. And this is also going to be important to use the kind of counterfactual ideas that we've been discussing for the evaluation procedure. And so I'll get into that now. I'll start by discussing a standard evaluation approach in this setting and why that's problematic and why we're going to want to use counterfactual techniques to roughly impute the missing outcomes and do something a little bit better. So the standard approach that I'm going to present for evaluation in this setting where we have these missing outcomes because we only observe the outcome under the historical decision taken. The standard approach would just say, okay, let's only look at the data where we have the outcome of interest, and we'll evaluate the algorithm on that. But the problem with that approach is that the data where the outcomes are available is not a random subsample of the data. It's often different in important ways from the full population on which we'd like to assess the algorithm. So in this stylized example, we might assess the accuracy to be 100% if we just looked at the rows where we have outcomes. But in reality, we'd be missing the fact that it would make mistakes on the rows where we're missing the outcomes. So, okay, so how can we fix this? So we're going to, I'll get into a formal problem formulation in the next slide, but at a high level here, I'll introduce the idea of counterfactual performance metrics, which are just going to replace the observed outcome Y in our standard metrics. So whatever metric you're interested in, like here I have true positive rate, we can replace where Y is with the counterfactual outcome. So the standard true positive rate is saying among those who had the observed outcome equal to 1, what's the likelihood our algorithm's going to flag them as high risk? And the counterfactual analog says among those whose potential outcome is 1, what's the likelihood the algorithm flags them as high risk? And, oh, sorry. So the difference there is just in that Y and YD. And we can do that for various metrics. Like here, I have an example for precision where we have the outcome on the other side of the conditioning statement. Okay, so a little bit more formally, the evaluation task is that we have a predictive model that I'm writing here as S hat of X. And we're interested in assessing how well it predicts the quantity, the counterfactual quantity that we want the algorithm to be predicting, expected value YD given X. And then if we're just interested in how well it estimates this mean quantity, we may be interested in the mean squared error. the counterfactual mean squared error, which I have written here. And in settings where this predictive model and Y are both binary, there could be other predictive metrics that we care about, especially if there are different costs associated with certain types of mistakes. So precision, true positive rate, and accuracy. So here, I just have done the counterfactual analog of the standard predictive performance metrics by replacing Y with the potential outcome. And then we run into the same challenge as we did in the learning step, that these are hypothetical quantities, but now we kind of know what to do about that. So I'll walk through the identification for precision. And the reason I'm choosing this particular metric is that it's really simple and it's really similar to what we saw to the learning part in the first slide. The others are just a little bit more technically involved because of where the conditioning statement happens. But we have details for those in the paper. But to get the key ideas, I think it's a little more instructive to work in this simple setting. Okay, so to identify counterfactual precision, we start by writing this metric using this function mu of x. And mu of x, it looks similar. It was the quantity we wanted the algorithm to predict, but now we're kind of thinking about doing this in the evaluation data. So we might think about, like, you would have built a model to predict that on some training data. And then now on the evaluation data, we're also interested in computing an estimate of this quantity. And so we write precision in terms of this function mu, because that will make this identification a little bit easier. Then under the assumptions we already discussed for the learning step, we can write mu as this is the identification that we already saw. We can write mu as the probability y equals 1, conditional on d and x. And then because we have written our counterfactual metric as a function of mu, then we can just plug in this identification to get an identification of precision. That is, to write this counterfactual precision in terms of things that we can actually estimate in the data. Okay, so now how do we do the estimation? This is a little bit more involved than what we saw for learning. So first I'll introduce like roughly conceptually what we're going to do and then get into the details. I'm just going to do a quick time check too. Okay. So here we have some stylized data where we have missing outcomes for rows 2 and 4. So we're going to try to guess what the outcomes are for these missing rows. And our estimates of those outcomes are going to have bias because we can't know perfectly what the outcomes would be, but we can use the observed outcomes in rows 1 and 3 to try to then estimate what our bias is on the unknown outcomes. And this is nice because because we have some information right in rows 1 and 3. We have seen outcomes, but we could also compare that against what we might guess those outcomes to be if we pretended like the data was missing there. And then that gives us an estimate of the bias. And we can use that then on average to get better estimates of our performance metrics. So that technique that we're going to do has a lot of names like double machine learning, targeted machine learning, doubly robust techniques, and it uses the influence function to derive this bias correction term, and it gets nice theoretical properties. There's been a lot of work on this in standard causal inference settings, and then our work, we take those kind of techniques from those standard causal inference settings and adapt them to the algorithmic decision support setting where the quantities we're interested in estimating are different from the standard standard causal inference quantities. Okay, so let's get into what this actually looks like to use double machine learning to estimate counterfactual precision. Okay, so we start by estimating these two. They're called nuisance functions because they're things that are useful for estimating the thing we really care about, but we don't directly care about them. And we've already seen these. So mu hat is the probability, it's like the analog to the thing we wanted to learn. It's the probability y equals 1, conditional on d and x. And then pi is the propensity score. And we can estimate those using whatever technique we like, ideally something flexible like machine learning or non-parametric regression. And then in the second stage, we're going to average these to get an estimate of precision. And so a simple way to do this would just be to take those estimates of mu and average them among everyone the algorithm flags as high risk. And this would give an estimate of counterfactual precision. But the problem is this would work well if we could perfectly estimate mu, but we can't in practice. There's going to be some bias there. So that's why we're going to add in this bias correction term. And the form of this came from the influence function for this metric. And this is adding this kind of inverse, it's this residual term where we're looking for cases where we've observed the outcome Y and comparing it against what the prediction was, and then inversely weighing that by the propensity score. And I'll skip this little bit about sample splitting. If there are questions about that, I could return later. I want to make sure we get to a few results and then open things up for questions. Okay, this has the particular form of these estimators for other predictive performance metrics. We walk through the one for precision. And if there's interest, I can describe what this looks like for some of the other metrics. It's conceptually the same as what we've done before, just some of the mechanics are a little bit different depending on the form of that predictive performance metric. The reason it's really nice to use this approach to estimate these quantities is because it gives us nice theoretical guarantees. We can get root inconsistency under some assumptions about how quickly the nuisance functions are converging that are relatively mild, and when we use sample splitting. And the reason that's great in practice is that means we can estimate confidence intervals on these performance estimates. So you can do like the standard Welt type confidence intervals to get an interval on precision if that's what you care about, or mean squared error if that's what you care about. Okay, so now we can see what this looks like in practice on some data. So we're going to compare a counterfactually valid model. We've already seen this actually against what I call here the invalid model, and this was the standard approach to learning. And we would hope that this evaluation approach should indicate that the counterfactual model is better. So as a reminder, the counterfactual model is going to be targeting this counterfactual outcome Y screen out, and this other model is going to be predicting this observed outcome. And we already saw some motivation for why I make the claim that the counterfactual model is better, because it shows the expected trend that aligns with the human assessment of risks, whereas the other model did not. Okay, so then what does it look like when we compute our counterfactual evaluation metrics here? So I am plotting the ROC curve here. We have false positive rate on the x-axis and recall on the y-axis. And this plot just shows if we did this using the standard approach. And this, so the standard approach, this was a few slides back, but this is saying we just look at the subset of the data where we have readily available outcomes. And here, it looks like these models perform comparably. The ROC curves are right on top of each other. But if we do a counterfactual evaluation of this, if we compute each one of these points, the false positive rate and recall, using the counterfactual approach that I presented, then we see a difference. We see evidence that the counterfactually valid model is better since it bends more toward the upper left than the invalid model. So that's good. That suggests that the counterfactual evaluation can distinguish better performing models in a way that the standard approach may miss. Okay, so that's a little recap. Yes. Okay, yeah, I'll just do the recap and then tie it up there and open things up for question. Okay, so in today's talk, we saw how in decision-making settings, we have missing outcome data because we only observe outcomes under the historical decision taken, and that can be different from the decision that we're interested in predicting outcomes under when we're building a model. And standard approaches that don't address this type of missing data can be misleading. So we use counterfactual techniques to address this. And we saw that there are some really key conditions under which this approach is valid, and that it's important to kind of reason about whether those hold in your particular settings. As a reminder, these are the conditions. And if there's interest in the Q&A, I can get a little bit more into what to do when there's unmeasured confounding. This first assumption is often the one that folks are concerned about in their settings. But I think this might be a good time to pause here and open it up for discussion so that we can answer whatever questions are top of mind for the audience. Thank you so much for your attention. This has been really fun.
Thank you very much, Amanda. Fantastic presentation. I've never understood this stuff before, so this is the first presentation where I've actually understood it. So thank you. Thank you very much.
Awesome. That feels good to hear.
Questions? Are there any questions? Feel free to raise your hand and I will call on you to... Oh, Daria, to get us started.
Yeah, I have a not very scientific and more like practical question. With this noisy proxy for unobserved outcomes when the call was screened out, so you use, if there was a follow-up call, like a second call to the same services, right?
Yeah.
So I was thinking, what if the person like answering this first initial call was assigned procedure to randomly sample from calls that otherwise they would screen out? Would it give you a better training data then for your data? Because you'll bypass the noisy proxy step then. But then I imagine that it's expensive to allocate this workforce just for, because I understand that it's unethical to test it on the other side. Like you can't randomly not investigate calls with red flags. But I would imagine it's less questionable practice if you randomly assign investigators to cases that you would otherwise screen out, but just for learning purposes. Suddenly you follow up just to generate the training set for your algorithms. Is it something that happens, or if it's not happening, is there a reason for that?
Yeah, that's an interesting proposal. As far as I'm aware, I don't know of that happening in practice, but it certainly could. And maybe I just haven't been in contact with those agencies. I think you sort of alluded to one of the issues that, yeah, there's some concerns about ethics. And I think you pointed out that it's more concerning to randomly not investigate cases where they're worried about harm. But I think there can still be some sensitivities in just introducing any kind of randomness in this process where it's already it's very sensitive, like very invasive process. And so I think the agencies, there may be some convincing to really try to convince them like that randomization is worth the potential political or like criticism that may come from doing something like that. Another issue is kind of more technical. So if I understood correctly, what you're proposing is saying like, re-referral is not really a great outcome. Somebody could call back and there is no harm, or there could be harm and they're not making a call back. So let's actually look into those cases, a random subset of them, and see what's going on. As soon as the county starts investigating, it does kind of affect the process. Because as soon as the county starts investigating, that means we can't really say what would have happened had we not investigated, if that makes sense. Now maybe that's okay. Maybe you say, okay, like, yeah, sure, the fact that a caseworker is showing up at someone's home may change parenting styles, but we're going to assume that's going to be like a small difference compared to what kind of harm is going on. But there are those kind of like subtle challenges in, if that makes sense, that as soon as we start having the county intervene on the system, it means we don't really know what would have happened had they not been intervening. Another option is looking at other data sources, like if the child was hospitalized for injuries that looked like abuse or neglect, and that is a much stronger signal of a harm and risk occurring, and it's one that we can see even if the agency isn't intervening. But fortunately, that occurs in such a small fraction of cases that outcome is not, like, there's not enough where we see that outcome occurring to actually use that to build a predictive model. But I think the agencies will use that as one of the metrics to evaluate the model and make sure that all of those cases are being assessed as high risk.
Daria, did you have any follow-ups?
No, it makes sense, actually. I didn't think, but it's also unethical to test in the other direction. I can imagine, I just imagine myself being those parents where the child services will show up. Definitely can affect the outcomes. Makes sense.
Yeah.
So Eric?
Yeah, thanks for the talk, Amanda. I guess a couple questions. Is there any guidelines around like sample splitting in terms of like, is the goal to maximize out of sample accuracy of the pi in the mu estimator and then pick the best one and say, okay, well, that's probably the best nuisance function to use. And then related, like if the treatment is, sorry, maybe you've mentioned this, but if the treatment is non-binary, it's continuous or something, can you just also again use the same like regression function instead, like the density of it? Any comments on just the kind of a practical stuff on the picking the nuisance one and then
Yeah, great. Okay, I'm glad you asked about this because I kind of skipped over sample splitting. But yes, so sample splitting is important. This means we need to estimate mu and pi, these nuisance functions in the first stage here, on a different random sample of the data than what we're using to compute our estimate of the performance metric in the second step here. And your question was about how to do that. So I think really like the goal is probably to regain data efficiency. So the problem with sample splitting is that, you know, if you split like half, then you're only using half the data to learn these regression functions and have to come up with your estimate. And so I think that the procedure I would advise is cross-fitting. So that means you split probably like 50-50. So you use half the data for step one to learn these regression functions, and then half the data to compute your metric in the second one step. And then you swap those. So then you'll use the second half to estimate the nuisance functions and then plug those in to get our estimate of the performance metric there. And then we'll have two estimates of the performance metric and we'll average those to get one that we say kind of use the full data. So that would be what I would advise there. I think that's what a lot of the literature recommends for other causal inference problems. And then for the other question about, so I focused mostly here as Y being binary because that meant we could look at some of these other metrics like precision. But if Y is a continuous outcome, you can do the same kind of procedure. So, you know, mathematically, we might not write this as Y equals 1, but the mu would just be the expectation of Y given D and X. And we would, estimate it using similar like machine learning, non-parametric regression techniques. It's actually sometimes more straightforward in that setting if you have a more normally distributed outcome to do the regressions.
Okay, yeah, that makes sense. Does it also work just as seamlessly if D is continuous?
No. So if D is continuous, then things are more I guess so if D is continuous, I think things would be more challenging because I think our goal would probably change in that setting. But I guess so very simply, if D were continuous, like let's say it's some kind of dose for medicine, but there was one particular dose that we wanted to know what would happen under, then that would be fine because here, you know, like if the dose was 100 milliliters of the drug, then that was a very precise decision that we're interested in predicting outcomes under, and everything goes through. But more realistically, in the continuous dose setting, we kind of want to say something different, like the quantities we want to estimate might be different. Like we might want to kind of estimate counterfactuals like within a region, or estimate ideally like the dose response curve. So it gets a little bit more complicated in that setting. We actually haven't worked on that, but I think that would be really interesting. I think everything you could kind of plug it through, but I think it would be better to do it for like the dose response curve versus pretending there was like one particular dose you were interested in. Does that make sense?
Mm-hmm. Yeah. Thank you.
David?
Hello. I'm wondering if you can use this method and flip around the zeros and ones and calculate local treatment effect. So look at the effect of actually having the intervention by the individuals.
Yeah, you definitely could do that. And I think that would be interesting. Yeah, so we said like there was one proposed decision we're interested in. You could say that was one, but then you could go through the same process for doing it for the other one, and then come up with a contrast, like looking at the difference or a ratio of those two. Yeah, sorry, go ahead. It sounds like there's another question.
And from a policy perspective, that would be interesting. Do these interventions help people? Do these interventions hurt people?
Yeah, I agree. I think that would be an important question. Yeah, and if that's what you were interested in doing, you certainly could do the approach you mentioned, but there actually are techniques that are kind of more optimally designed for estimating treatment effects that would estimate them in one go versus kind of doing those two separate pieces and then just computing the difference. And the high level reasoning for that is that sometimes the treatment effect curve is like lower dimension, like it's more smooth than the individual pieces that we're estimating here. So if you come up with techniques that can take advantage of that smoothness, you can estimate them better. And yeah, so that's just a side note that if that's what you wanted to do, I think there are probably better methods that would directly go for that versus doing my procedure twice. This was really designed for these settings where they're building algorithms to predict outcomes under one particular decision. But I definitely hear what you're saying, that especially if we're interested in like, you know, how well are these systems functioning, even looking at like, you know, how is the algorithm improving things, then looking at things like treatment effects are going to be really important to do.
Thank you.
Yeah, thanks for the question.
If anyone has any questions, feel free to raise your hand and I'll call on you. Maybe while people are thinking, Amanda, could you talk a little bit about some of the data challenges involved in dealing with these types of data and managing it, whether that's privacy or the size of it or any of those sorts of things that you faced?
Yeah. Yeah, definitely privacy. I mean, so one of the challenges in working with this kind of data is that it's, you know, it's not publicly available. The county is very kind of protective of who has access to it. And so that means it's exciting when we are able to access this data, but also means that it's not when you put a research paper out that has this results, that's not something that other people can replicate. So to address that, we also, I think in most of the papers accompany it with some synthetic results that can be replicated. Another challenge that I would bring up was that there can be, with these kind of real world data, there can be kind of distribution shifts due to policy changes that matter significantly. So an example was, so this Allegheny County is in Pennsylvania, and in Pennsylvania, I think it was around 2015, they had a big change in the mandatory reporting. So they really expanded who was a mandated reporter. This was in the wake of the Jerry Sandusky, when all of that came to light. So they expanded who was a mandated reporter to include like a broad class, teachers, coaches, clergymen, medical professionals. I mean, some of those were already mandated reporters before the policy change, but essentially because of this big expansion and who is considered a mandated reporter, this doubled, or maybe even more than that, the call volume to the calls. And so this means that the kinds of data that we're observing after a policy change is very different from what happened before. So that meant that we can't really use the data before this policy change to build a model that will be relevant after that. So that kind of policy change really divided up what the data looks like. And I think it's kind of an interesting thing to reflect on, because that was a very big policy change that we could kind of pinpoint and know is something we needed to address. And you could observe that big increase in the number of calls coming into the hotline, but there probably also are much smaller, like harder to detect distributional changes that happen over time as well. And I think that's a really interesting challenge for an open problem for machine learning in these settings, is how do we monitor their performance once they've been deployed, and kind of identify when distributional changes are becoming big enough that we may want to retrain the model, or at least reevaluate it and make sure we're still comfortable with using it, knowing that the performance now is different from what it was when we evaluated it before deploying it.
Yeah, absolutely. It's interesting. You've got almost like a big data, but also a small data problem. You've got big data problems, but also small data problems.
Yeah.
Are there any other questions from folks? Maybe just briefly, where would you see what other applications would you see for your methodology and approaches? Where else could you go with this in the next few years?
Yeah, that's a great question. I am interested in seeing how well these kind of techniques apply in other settings. Particularly healthcare is one area that I'd like to work on. So looking at clinical decision support algorithms, when medical professionals are using machine learning algorithms that make estimates of things like whether the patient will be readmitted to the hospital or other bad outcomes under some proposed intervention, and using that to inform their care decisions. I think that would be a setting where, structurally the kinds of issues I talk about apply, that we have these missing outcomes because of we only observe outcomes under the historical decision. But it's no longer reasonable to make that assumption about no unmeasured confounding. So in the child welfare setting, because it's a very kind of controlled setting where we know what the call worker is making their decision based on, that's a little bit easier to justify. But in other settings, especially healthcare, we don't have that equivalent like amounts of the data recorded. Like the doctor is probably observing a lot of stuff in their interaction with the patients that aren't reflected in the case notes. And so then it becomes a lot more challenging, like what kind of assumption are we comfortable making there that will still enable us to kind of say something specific in our predictive algorithm, and something specific about how well that algorithm might perform. And so that's something that we already started working on in this kind of follow-up paper that I briefly alluded to at the beginning of the presentation. So we develop a procedure here that has a milder version of the we're not requiring there to be no unobserved confounding, but we're requiring there to be some limit on the amount of unobserved confounding. And I think it'd be interesting to work with practitioners to see whether these assumptions are something that they can reason about and that seem reasonable in that setting, or if like a different approach is needed for that to actually be something that can be used in those settings.
Excellent. Thank you very much. So I'll just say thank you once again for a fantastic presentation. I didn't mention at the start, but you one of your many accolades is your rising star in EECS, and I don't know who I have to talk to, but that should obviously just be changed to a superstar. So thanks very much. Looking forward to your research, and yeah, have a nice day. Rest of the day, everyone.
That's so kind of you to say. Thank you all so much for joining. This was a pleasure.